Good afternoon, everyone. My name is Shancong. Today, I will present my research of the heavy traffic queue-length behavior in a switch and Markovian arrivals. This is a collaborative research with Professor Siva, Theja, Maguluri, and we are from School of Industrial Engineering, Georgia Tech. Big data and machine learning revolutions are powered by large-scale data centers. So with the growing size of data centers, design and operation of such data exchange networks are very important. Input queue switches are building blocks of any data network. The goal is to design a network that is logically equivalent to an input queue switch. We are still far away from this goal, and today's data centers have a hierarchical network, and the switch is an approximation. So huge switch interconnects the servers, and when the data is sent between servers connected by those switches, certain constraints need to be met, and I will explain this later. However, in today's talk, I will ignore the details, and we approximate the data center to a switch. So the question is here, given this switch, how do you schedule packets inside it? So I will explain this in next slides. Let's consider n by n switch, and the scheduling algorithm is actually the MaxWeight algorithm. So a matrix of queues operating in a discrete time is the n by n switch. Each rows are input ports and columns are output ports. Packets arrive according to an i.i.d random process. Each packet needs exactly one time slot of service. And the key constraint here is at most one queue from each row and one from each column can be served in each time slot. And the question now is, which set of queues should be served in each time slot? There is a very famous scheduling algorithm that is called MaxWeight algorithm. And it has been proved that the MaxWeight algorithm under the i.i.d assumption is throughput optimal. Understanding the queue length performance in such a system is very challenging. Therefore, researchers usually use the asymptotic analysis method to study this system. That is called the heavy traffic analysis. Let the total arrival rate to each row and each column to be 1 minus epsilon. That is, when epsilon becomes smaller, that means the arrival rate approaches the service rate. Here we are interested in the case that if we increase the size of the switch, that is n, or we decrease the epsilon, how does the expected steady-state queue length scale? Here is a very famous conjecture that gives the limiting scale expected sum of queue length. And recently, it was proved by Maguluri and Shancong in 2016. However, their proof is under i.i.d arrival assumption. However, let's look at the workload patterns in a real data center network. Recently, there are some researchers studied the workload patterns I listed here. One is in 2019 and another one is in 2020. Let's look at it. First, we can say that the workload patterns can be on and off. They can be growing very fast, or they can be unpredictable bursting, or they can be predictable bursting. And another thing is that we can say that the workload patterns are highly correlated across time. So that means in real data center networks, the arrivals are not i.i.d. So how do we analyze the performance of such data center networks under non-i.i.d arrivals is very important, right? So here we use the Markovian modulated arrival to model this process. So what is Markovian modulated arrival? We assume there is an underlying Markov chain. It is n by n dimension, and we assume that it is finite state space, it is irreducible and positive recurrent. And we also assume that there is a bijection. It is a function that link the arrival process with the Markov chain. That means the arrival process is determined by this Markov chain, and we let the expectation of the steady state arrival process to be lambda. Because we know that the Markov chain is a finite state space, irreducible, and positive recurrent, then that means there is a steady state distribution, right? And we define the sigma ij square to be the variance, and it is defined as the summation of autocorrelation functions across time. The autocorrelation function is defined as here. Actually, it is the t-type autocorrelation function of the arrival process. We have to make an assumption that when epsilon goes to 0, this autocorrelation function converge to a steady state autocorrelation function. Next, I will state our main result. This result answers the question that what is the behavior of the system under non-i.i.d. arrival case. The main contribution here is that we extend the analysis of the system from i.i.d. arrival case to Markovian modulated arrival case. Here is the main theorem. It says that in steady state, the limiting scaled expectation of sum of Q length equals to 1 minus 1 over 2n times sigma square. Here, n is the dimension of the switch and sigma square is the variance we defined before. So what does this result mean? It means that for the MaxWeight scaling algorithm, even in the Markovian modulated arrival case, the Q length is within a factor of less than 2 from a universal lower bound. So I list the universal lower bound here. Next, I will give our proof techniques on how to deal with the Markovian modulated arrival case. The key proof technique is the dynamic m-step Lyapunov Drift Method. Our method is an extension of the drift method. So the first step is to set one-step drift of the Lyapunov function to 0. That is expectation of qt plus square minus qt square equals 0. And then we expand this equation. In the left-hand side, we can get the scaled Q length, and in the right-hand side, we can get some other terms. Let's look at the first term, the red term here. In the i.i.d. arrival case, the Q length and arrival are independent. That means this term is equal to 0. So in the single server queue, we can get the famous K-mass bond. And in the switch system, we can get the result in Maguluri's research. However, in our case, when the arrival process are Markovian modulated, that means the Q length and arrival are not i.i.d. anymore. This becomes the main challenge. So how to deal with it? We propose that we can use m-step method. We convert the one-step drift to m-step drift, and we expand it. We can get the following equation here. Here, in order to deal with the qt and at plus m, their correlation, we use the finite times mixing. We notice that as m goes to infinity, their correlation actually decreases exponentially fast. So this is a key observation. Once we have this observation, we can pick m as a function of the heavy traffic parameter epsilon. And when we let epsilon goes to 0, at the same time, m will goes to infinity. That means in this limiting process, the correlation as m goes to infinity, actually decreases and then it becomes a 0. Use this technique, we can get mainly two results. The first result is the limit Q-length of the single server queue and also its distribution. And the second result is the result we stated before for the switch system. Next, I will give the conclusion and our future work. In this research, we analyzed the heavy traffic behavior of a switch operating under the MaxWeight algorithm when the arrivals are Markovian modulated. Notice that the arrivals are not i.i.d anymore. And the key challenge here is how to handle the Markovian correlations. Here, we proposed a dynamic m-step Lyapunov Drift Method, and we also exploit the geometric mixing of the Markov chains. For the future work, we have two parts. The first part is that we want to generalize the result to the so-called generalized switch models. And the second part is we want to establish the generality of Markov modulated arrivals in discrete time systems. This is my presentation of our research, and please let me know if you have any questions. I will be really happy to answer. And thank you.